Hi everyone, we are Group 2 and we are here to present our exploration into the YOLOv7 object detection model, which is a state-of-the-art CNN-based model for real-time object detection. Throughout this presentation, we'll look at the original paper we worked from, how the YOLO model works, the dataset we used, the model's architecture, some proposed modifications we have, and the results of our experiments with them. So first, we have to discuss the original paper that we worked from. The original YOLOv7 paper sets a new benchmark for real-time object detection, both in terms of accuracy and inference time. By building upon the YOLO family's tradition of speed and accuracy in object detection, YOLOv7 introduces a few clever training tricks to surpass its predecessors and competitors. This is all thanks to what authors call a set of trainable bag of freebies, implemented on top of the traditional YOLO model to enhance accuracy without increasing inference time. As you can see in this graphic, YOLOv7's average precision over inference time, which is a common measure of accuracy over detection speed, consistently produces equally accurate or better results at nearly 120% faster speeds compared to previous YOLO models. To understand how this is all accomplished, we first have to understand what the YOLO model is. YOLO stands for You Only Look Once, referring to the single forward pass needed to produce an output. Unlike traditional two-stage image detectors that have a computationally complex and separate region proposal stage and then a classification stage, YOLO does object detection in a single forward pass of neural network. Simply through many layers of convolution and pooling, the image is divided into a set number of subregions. The subregions then individually propose a classification and a possible bounding box for this classification. From here, the model is able to determine the most likely bounding boxes for an image with their corresponding label. Like here in this picture, the most likely proposed bounding boxes correctly contain the dog and the person within them. This design makes YOLO-based models extremely fast, which is imperative to real-time detection while maintaining competitive accuracy. Most importantly, deep neural networks like YOLOv7, the dataset used, must be comprehensive and accurate. This is why YOLOv7 is trained on the MS-COCO dataset, a trusted, large, and diverse set of about 118,000 images with 80 object categories. Here are a few examples directly from the dataset, such as a person on a surfboard, a person throwing a baseball, cars on the road. To further boost generalization, YOLOv7 employs multiple data augmentations, which are pre-processing techniques to make the dataset more diverse and varied. Techniques like mosaic and mix-up combine multiple images, forcing the model to learn from complex scenarios. While simple augmentations such as random flips or color jitter also prevent overfitting by exposing the model to a broader range of image conditions.
These data augmentations are extremely powerful tools for getting more learning capacity out of a given dataset, as it is expanding the number of contexts these objects that may appear in. Here's an example of an image after the mosaic and mix-up data augmentation, which takes a series of images with labels and produces a single image containing all of them stitched together. As you can see in the slide, many images with their labels have been resized, stitched together, and even overlaid on top of each other to create an extremely diverse image comprising many objects. This would be an example image that the model is looking at to learn from. Other examples could be rotating the image or scaling them, cropping out different areas, and these all contribute to the learning process. The general YOLO model architecture has three main components. First, the backbone, which is a CSP-based network, extracts as many rich features from the image as possible, turning a raw image into many layers of interesting features to further examine and classify. Next, these features are fed into the neck, which combine them at multiple scales, ensuring the objects large and small are well represented and do not overshadow each other in importance. Finally, the head uses the multi-scale features to predict object bounding boxes and classes. YOLOv7 improves upon the architecture with their trainable bag of freebies, which are a set of tricks that can be implemented to increase accuracy with no extra cost to inference time. These include the mosaic and mix-up data augmentations discussed in the previous slide, which force the model to learn more using the same dataset but altering their contexts. But it also includes dynamic label assignment, which ensures the predicted bounding boxes are matched to the correct ground truth, which streamlines the learning process to keep the model from learning from slightly incorrect predictions. Here's an example of YOLOv7 in action. On the left is the unlabeled input image, and on the right is the output from the model. YOLOv7 quickly identifies multiple objects, drawing bounding boxes and assigning class labels in real time. Each bounding box, you could see, has a number associated with it, which is its confidence score. So for example, the vase in the bottom right corner here was correctly identified, and the model has about 75% confidence in its classification.
Given this powerful and fast model, how could we attempt to improve upon its approach? Analyzing how YOLOv7's main improvements to the family involved incorporating new training tricks, as we discussed before, we began to investigate if the changes to the architecture itself could be optimized further. Thus, we have proposed two modifications to the YOLOv7 architecture. The first modification proposed was to replace all activation functions in the convolutional layer with a slightly smoother function to hopefully improve gradient flow through the network, possibly leading to an increased representational capacity. And the second was to add an extra convolutional layer to the front of the backbone, hopefully to enrich the initial future maps fed into the neck, giving the model a... Now let's examine the first modification, which was replacing all of the activation functions. Appended to each convolutional layer in the network is a CILU layer, or a sigmoid linear unit, which smoothly transitions from negative to positive values to preserve small signals better than traditional ReLU variants. Given this key characteristic, our proposed modification involves switching out this GEL with the GELU, switching out the sigmoid linear unit with the GELU, or Gaussian error linear unit. This new function is considered even smoother, as you can see on the right. Our intention with this new function is to yield more stable gradients, which could unlock marginal gains in convergence speed and an already optimized model. In practice, these ideas didn't exactly hold true. To speed up training, these experiments were run on a small subset of COCO, which was each included about 5,500 images. And after about 40 epochs of training, the loss trend appeared to be nearly identical to the original model. The only detectable difference being in the objectness loss, which is the loss responsible for accessing the model's ability to determine whether or not an object exists within the region. Early on in the training, the GELU seemed to provide a bit more stable and consistent decrease over time, but after about 30 or so epochs, the losses became identical across activation functions. In reality, this can be expected for a model like YOLO that is already so optimized in terms of the architecture, and making such a small change in the activation function may not produce much of a difference.
So in addition to switching the activation function, we also introduced a new convolutional layer at the very start of the backbone. The idea is to give the model an extra step of initial feature extraction before it proceeds through the standard layers of the network. By doing this, we aim to capture more detailed, low-level features such as edges, corners, and textures, which form the building blocks for recognizing more complex object patterns later on. If we are able to create more meaningful feature maps from smaller and less noticeable objects, downstream classification may actually be able to detect them. And thus, in theory, this enhanced early feature set can help the model more accurately localize and classify objects, especially the smaller ones or more challenging ones that benefit from a richer initial representation. Again, with our reduced dataset over 40 epochs, we did not see any improvements in terms of loss or accuracy. In terms of loss, again, no noticeable changes across implementations could be seen apart from objectness. As you can see in the graphics here, the new architecture more than doubled the objectness loss over the 40 epochs of training from non-pre-trained weights. We think this is another symptom of trying to change an already established architecture that has become so optimized and tailored over the years. The extra layer has most likely enriched the feature map, but too heavily by introducing extra emphasis on small details. This emphasis was intended, but because the downstream operations are so optimized for the original feature maps, detection has classified too many background features as objects. In turn, this extra feature extraction may actually prove useful once the downstream layers adapt to the change, but this would require training over the full COCO dataset over hundreds of epochs. Finally here, we have compared the accuracy metrics across the original model and a model with both of our modifications implemented. Relevant metrics used in a model like YOLO will be precision, recall, and MAP. Here, YOLOv7 actually uses two different MAP metrics, which reports mean average precision at different predicted bounding box thresholds. Again, this is after training the model from scratch with a reduced dataset over only 40 epochs, so the accuracies will not reflect the true accuracies of the published model, which boasts an industry-leading MAP of 60%. As you can see here, the modified model was not as accurate in terms of MAP, which best reflects the fact that the architecture has become highly optimized over the years. So much so that this latest model, YOLOv7, doesn't even change the architecture. It simply improves upon the training methods. What we learned from our experiments is that if there is any gains to be made upon the YOLO architecture, it is best to look outside of the architecture first, such as training methods, before trying to modify the architecture that has been worked on so closely for so many years. And finally, here are some references used throughout this presentation. Thank you so much.